Electrochemistry. Really what this is tying back to is a lot of energy and how we can manipulate energy to our favor. So we'll talk a little bit about batteries. I don't think we're going to talk as much about, actually, I think there are some slides that talk about solar panels a little bit towards the end. But for the most part, our primary focus within electrochemistry is dealing with batteries. So why batteries? Okay, one of the biggest issues when we talk about the transition away from fossil fuels is where do we store that power? So if we look at hydroelectric, that one's not too bad because the water just runs. As long as we've got generators catching that water or in the path of that water, we're going to get pretty constant power. We look at wind. What happens when the wind disappears? Okay, if the wind goes away, you no longer have that energy source. And in the same kind of deal with solar, half of our day we have no way to collect solar power, at least within an individual location. So we need some place to store that energy, and that storage is usually going to come down to batteries. So we need some better battery technology. And when we're looking at batteries, they involve the transfer of electrons from one species to another. So if you remember from 151, hopefully you had single replacement reactions. Does that ring a bell? Okay. Those were all examples of reduction and oxidation reactions. Theoretically, you also talked maybe a little bit about redox in 151. Yeah? Ish? No? Okay. Every class is slightly different, but ideally you would have had some context there. Okay, but those are all talking about that transfer of electrons, and as we transfer electrons, there's an energy shift as well, or energy release. If we can control how the electrons are transferred, we can harness that for batteries. Biological systems also equally harness that when we talk about the production of energy. We decompose glucose, or we look at the decomposition of glucose. We control that process in our cells to produce energy. That energy gets stored into ATP, and then that moves into a biochemistry class if you wanted to look at that. Okay? If you look at how muscles function because of the flow of ions across an individual channel. Well, ions are a charge. That flow can contribute to motion, and that is technically an electrical flow. Okay? So lots of different systems use redox reactions. So we need to understand them, and that's where we get into some terms. So oxidation is a loss of electrons. Reduction is a gain of electrons. Okay? To help with that, you'll hear various acronyms out there. And because none of you have had chemistry with me ever before, I'll get a little bit up on a soapbox here because it's something I frequently do. And biology has a horrible acronym because they go through and use something known as oil rig, which is flippin' stupid considering the whole point of their class is talking about living organisms, and instead they use dead organisms to explain the transfer of electrons. Okay? Even then, when they talk about it, oil stands for oxidation is loss. Loss of what? Peanuts? Okay? Makes absolutely no sense. It's a stupid system to memorize, and I hate it, to put it mildly. Right? Instead, what I would prefer that we go through and memorize is if we look at a loss of electrons is oxidation, we have spelled out LEO, also known as Leo or a lion. Okay? Leo is some languages prefix for lion. Okay, so we could say Leo the lion says, what do lions do? They grr. Okay, and this will help to associate the loss of electrons being oxidation, the gain of electrons being reduction. Okay? Those ties become very, very important because when you go through and look at a chemical reaction, you should eventually be able to track that electrons have been transferred. Okay? But the species that transferred, which one accepted, all of those kind of things, we now want to be able to talk about without having to talk about the transfer of electrons. And that's where we get the terms of oxidation and reduction, because we're using that as part of our language to simplify our language systems. Kind of, sort of? Okay. Where are the terms oxidation and reduction coming from? Just sort of a bit of trivia. I would argue oxidation was probably the first one to come about. Anything sound like oxidation? Oxygen, right? And when we talk about our exposure to these reactions, we've seen rust a whole lot. That rust is an oxidation. Why is it an oxidation? What happened to the iron when it rusts? So we could talk about the electrons, but that was really hard hundreds of years ago. Reacted with oxygen. And it was the presence of oxygen that triggers our first kind of calls for oxidation. Oxidation is technically referring to the increasing in bonds to oxygen. Okay? That's where that term is coming from. The reduction term is looking at the reduction of bonds to oxygen. So if we're referencing it historically, that's kind of the context behind that. That is a historical reference, and as a historical reference, it of course changes and gets adapted as we learn more information, because oxygen isn't necessarily always involved in a reduction and oxidation reaction. It just happens to be involved in a lot of the very common ones we see because oxygen's everywhere, okay? And oxygen is an exceptionally reactive reagent or chemical that facilitates a lot of these electron transfer pathways. Okay? So that then navigates us to how we track the transfer of electrons. So one of the things that we'll go through and do is identify our oxidation numbers or oxidation states. These things get assigned to an individual atom. Okay, so every atom on your reactant side gets an oxidation number. Every atom on the product side of your chemical reaction gets an oxidation number. And so what you would go through and do is look at that atom and how its oxidation number changed through the chemical reaction. If it changes, we can now say, well, how did it change? So if we went through and looked at the examples sort of shown below, we're looking at a metal. That metal has a zero oxidation state. We'll come back to how we know that in a little bit. Okay, but it starts at a 0 and becomes positive. How could we go from a 0 to a positive? What had to happen? It had to lose an electron. That's it. And so if it's lost an electron, we would then say that that was oxidation. So if we can track our individual oxidation states on our individual materials, we can go through and identify how electrons were transferred through the course of an individual reaction. One of the things that frequently shows up or potentially shows up is that we see this presence of an electron in our chemical equation. How often have you seen electrons in a chemical equation? Never. Why not? Why have we never seen an electron in a chemical equation?
Chemical equation. Is an electron a chemical?
It's an interesting approach to that question. For the sake of argument, let's say yes.
Okay.
How stable are electrons? Not stable at all. They are so unstable that when we find electrons, where are they near? They're near protons. They're near other things to help stabilize that charge. So electrons are ultimately very, very unstable and very reactive. Because they are so reactive, we don't see free electrons. Okay? And if we talk about electricity, that's the movement of electrons, do we get free electrons? we don't, they're stuck to the wire. Only when we provide a path for where that electron can move to so that it can react with something else do we allow it to see that motion. Okay? This is why you don't stick forks in electrical outlets, because the electrons will pass through you to find something to neutralize. Okay? So electrons are very unstable, then why do we see our expressions here with our oxidation and our reduction with electrons in them? Why don't I just write this out as m plus a, m plus a minus? The sum of those two equations. Why don't I do that? An obnoxious trick question. We do. That's exactly how we write it. Okay, what we don't do is write out the expressions where we see the individual electrons in the equation. Okay? Why not? Well, in a lot of our individual cases, we aren't seeing electrons in our chemical expressions, so we don't need to worry about it. Okay? We just decide that we don't have to. Right? Here, because we're very specifically talking about how the electrons are changing their locations, what we've decided to do is split the overall equation into what's known as half reactions, because half of the reaction is doing an oxidation, it's losing electrons, and the other half is gaining electrons. By splitting it into those halves, we can now study each of those halves somewhat independently and come to different conclusions and quantifications and all sorts of other fun jazz. Kind of makes sense? Okay. Which then takes us to how do we determine oxidation numbers? Okay, so I'm curious, whoops, that's not the right button. Let's try that one. How would you go through and assign an oxidation number? I genuinely don't know what you've seen in 151, so this would be the opportunity. And maybe you don't like structures, so how about carbon dioxide? How do you determine the oxidation numbers for carbon and oxygen?
You break them up into individual atoms. And they all have charges.
Okay. So what charges are these going to have? So 2 what? Plus 2? Negative 2? Thank you for being brave, by the way.
Because it's going to be based off the negative charge.
Okay. So keep going. Say again. Plus 4. All right. How do you get a plus 4? Valence, so oxygen's a plus 6. How do you get oxygen as a minus 2?
Counting from the normal gas is 0. Or 8, sorry, is it 8?
Oh, okay. This is fine. That's fine. We're just trying to push on it and see what you have already. All right? And so officially, one of the good responses or valid responses to this would be, I don't know. I never learned that. That's fine. Okay? And since I have no context of what you saw on 151 or 130 for that matter, that's a valid answer. Mildly grumpy, but not at you, grumpy at your past instructors. So don't stress about that. Okay? So we're hearing one thing about going to pulling the numbers off of our periodic table. The numbers off of our periodic table trying to achieve the noble gas, okay, is looking at the charge or our common ionic charges. Okay? So if we leaned into oxygen to look like a noble gas, what could it do? to look like a noble gas. What noble gas do you think oxygen would try to look like? Do you think it would try and look like radon? No, why not? Way too far away. Okay. So what should oxygen try to look like? Neon. Right? What part of oxygen's character can it change without changing its identity? Only the electrons. And if we say charge, we've got to be careful because there's two things that contribute to charge. What are the two things that contribute to charge? Electrons and protons. Okay? So I could go through and change the number of protons for oxygen, but then would it be oxygen anymore? No, that's changed its identity. We can't change the identity of the element. Okay? So how could we make it look like neon? Change the electrons. How many electrons does neon have? 10. How many electrons does oxygen have? 8. What could it do? Add 2 electrons. And that's how we would get our common ionic charges. Okay? Our common ionic charges are powerful, but they only work when we have ions. How do you know you have an ion? As a hint, it's in the name. You have ions when you have ionic bonds. If you don't have ionic bonds, you don't have ions anymore. Okay? That sets up a problem when we look at carbon dioxide because it's not ionic because it doesn't have a metal and a nonmetal. They're both nonmetals. That sets up an issue that we now have to create a new system. Okay, so instead of looking at charges, what we would shift to is now looking at oxidation states. Oxidation states are very particular balances of protons and electrons on an individual atom. Sometimes the oxidation state matches the charge. Sometimes it doesn't. Okay? So for instance, we've got an example here where we're saying the carbon is a +4. Why did you say carbon was +4? Give it to me again.
Its valence is plus is 4. It's +4.
But oxygen's valence was 6,
Or sorry,
and you said oxygen was a -2. So how did you get from a 6 to a -2?
subtract the number of electrons from valence.
Oxygen has 8 electrons to look like neon. What do we need to do?
No, yeah, it's
Gain 2 electrons. For carbon, has 6 electrons. What noble gas does it want to look like? Neon? Okay. If carbon has 6 and it looks like neon, what does it need to do? Gain 4 electrons. If it gains 4 electrons, what would its charge be? Negative. That says +4. How'd you get +4? You're not wrong. How'd you get +4? Carbon's a nasty atom, right? Because it could gain 4 electrons to look like neon or lose 4 to look like helium. So depending on your system and what that carbon ion is bonded to, it would change its charge state. This is why typically when you're told to go through and deal with ionic charges, I know you're never told to memorize things, but if you've been told to memorize charges, you typically are not told to memorize carbons. Because carbon is variable. It can switch depending on its individual environment. How can we see evidence for that? Well, is it +4 here? Yeah, how do you know that?
It's right there.
Just because I wrote it doesn't make it true. Why is the carbon being a +4 here make sense to you?
Because you have 2 oxygens, so they'll gain, each one will gain 2 electrons.
If I have 2 oxygens and each of them has a -2 charge, I have 1 carbon and it has an unknown charge. When I add that all up, what must that equal?
0.
Why does it have to equal 0?
You can't like gain or lose electrons.
False though. Why does it have to equal 0? You have to go back to your original molecule. In the upper right-hand corner, we look at the charge. When we look at the balance of protons and electrons on each of the individual atoms, that must sum together to equal the balance of protons and electrons on the overall molecule. So in this case, the overall charge is 0. What can I now go through and do? I can solve for x. X minus 4 equals 0, and I get x equals plus 4. So you are 100% correct. Does this mean carbon always has a plus 4? No, because we could quickly go through and switch to a new compound. Let's pick carbon monoxide. Now is the carbon a plus 4? No, because if it was a plus 4, what would happen? What would change about my drawing? Upper right-hand corner, I would need to see a plus 2, because I have one carbon with a plus 4 plus the oxygen, one oxygen with a negative 2. That math says I get a plus 2. Okay? So what I'm trying to point out here is that we have a very delicate balance between oxidation state and charge. So depending on how much work you've spent on memorizing charges, you're going to have to be real careful in applying those charges to individual oxidation states. Typically, what you're responsible for is looking at a chemical formula and determining oxidation states from said chemical formula. Okay? Based off of the examples that I've seen through the slides, things are going to get weird for you because we're no longer looking at formulas. We end up looking at structures. And if we go through and look at that structure, how could we possibly determine the oxidation states? We have to evaluate the bonds. Okay? We have to evaluate the balance of electrons for each of those individual atoms in each individual case. So if we look at the oxygen comes in with 6 valence electrons. It contributes 6 to the overall molecule. But now we look at the molecule and says, well, where did those electrons actually disperse? Okay? And if we go through and look at this molecule, how many electrons are owned by oxygen in the molecule now? We might say half the bond. Do you mean oxygen and hydrogen equally share the electrons? Oh, no, they don't. How do you know they don't? Say it again louder. That wasn't much louder. Electronegativity. Oxygen is more electronegative than the hydrogen, which means how many electrons does the oxygen own? There's 4 from the lone pair. What's happening with the bond with the hydrogen? It's closer to the oxygen, which means
6.
I'm at 6. How about the bond between the carbon and the oxygen?
8.
Oxygen's more electronegative than the carbon as well, which means the oxygen owns 8. What's 6 minus 8? Negative 2. And in this case, what do we notice? The oxygen comes in with the exact same oxidation state as its charge. Why? What's determining our oxidation state? Electronegativity. And what's special about oxygen? It's the second most electronegative element on the periodic table, which means in almost all cases, when I bond oxygen to something, its oxidation state is going to be negative 2. Does that mean it will always be negative 2? No. When will it not be negative 2? When it's with fluorine, it's going to change its oxidation state. Awesome. There's one more exception. When it's with oxygen. Because in the case where oxygen is bonded to oxygen, are they sharing the electrons? Yeah, they have equal electronegativities, which means that bond is going to split 1 to 1, not going all to 1. So if we understand our electronegativity trends, we can start to predict our oxidation states. And what we're starting to do is introduce a new formula that can come out of this. Our oxidation state is equal to the number of valence electrons minus the number of electrons each atom has in the molecule. Okay? Said potentially another way, the electrons owned. Okay? That's how we determine our oxidation state. So, we've got methanol. We just looked at oxygen. Should we look at the rest together? Or do you think you got it? You got it? Cool. Spend a second. Figure out the oxidation states for the carbons and the hydrogens. Are we ready? Let's take a look at the purple hydrogen. How many valence electrons does hydrogen bring in? 1. How many electrons does it own? It only has that one bond next to it. How many electrons does it own? 0. It owns none of those electrons because the oxygen is taking it away. Was it minus 0? Yeah. Which means the oxidation state for that hydrogen is +1. Okay. We now have the option of choosing between our carbon and the other hydrogens. Right? I would make the argument that all those blue hydrogens are now identical to each other. They're all connected to a carbon, so all I have to do is address one of them and we should be good. How many valence electrons does hydrogen have? 1. Minus, how many electrons does it own? We're looking at the whoops, that's an eraser. We're looking at the single bond to that carbon. Which one's more electronegative, hydrogen or carbon? Carbon, which means the hydrogen owns 0. This equals +1. What happens with our carbon? Carbon brings in 4 valence minus. Okay. So go through. Carbon's going to be a bit trickier than the hydrogen is for sure. Roughly the same trickiness as our individual oxygen. Look at each bond. So look at the bond to the bottom. Does the carbon take the electrons away from the hydrogen? Yeah, it's more electronegative than the hydrogen. So that's 2. How about the other one? That's another 2. 2 plus 2 is 4. Plus another 2 from the other hydrogen, 6. What about the bond to the oxygen? Oxygen is more electronegative, so oxygen takes all of those away. Which means how many electrons does the carbon own? 6. And 4 minus 6 would be what? -2. Do we have an internal check that we can run? What's the internal check? I don't know what that means. If it works for you, good.
If you add them all up, should they just equal 0?
If we add up the oxidation states for every single atom, we should get the overall charge for the molecule. Do you see any charges associated with this molecule? No, which means when we add up all the individual oxidation states, we'd better get 0. So a -2 and a -2 is -4 plus 2. Isn't that -2? I have to acknowledge that I have multiple hydrogens coming in at a +1. So does the charge balance out? Yes. Okay. Charge is something that is only is specified to anything. That charge can be something that's shown for a molecule. It can also be shown for an atom. Oxidation state is a little bit different, or oxidation numbers are a little bit different. They are only specified for an atom, and that's it. Right? So there are cases where the oxidation state and the charge are the same because the thing you're looking at is all by itself. Right? If it is in a larger compound, then you have to be a little bit more careful with it, and you're going to have to break it down into those individual systems. Kind of make sense? Okay. So one of the things that becomes important is knowing your periodic trends. What is your trend in electronegativity? Helium is the most electronegative? Okay, you said top right.
Well, except the noble gases.
Oh, okay.
My bad.
It's Me being obnoxious. Thank you for playing along. The noble gases have effectively no electronegativity. We're now looking at fluorine being the most, and it trends lower left being the lowest. Okay? If you go through and actually look up a table of electronegativities, a couple things will become apparent. Number one, we don't have electronegativities for every atom. Why not? Kind of has to do with it hasn't been studied. It's been studied enough that we have the element. What is electronegativity defined as? What is the definition of electronegativity? This becomes a critical definition, particularly for those who have to advance into organic chemistry. We talk about the ability to attract electrons. You're only half right. Because when we talk about the ability to attract electrons, that's actually electron affinity. We talked about that in 151. So what is electronegativity? How is it different from electron affinity? It's all about what electron. Electron affinity is talking about attracting an electron from the vacuum. Electronegativity is very specifically referring to bonding electrons. Why does that become important? Why do we not have electronegativities for all of our elements? Well, some of those elements are so unstable. How many compounds do we have? 0. And if we don't have compounds, we can't see how they have a difference in electronegativity. There's nothing to compare to because there's no bond for us to actually study. Right? So that's one thing that'll pop up. The other thing that you might see pop up is a variety of different numbers for the electronegativity. Electronegativity is starting to become more clearly defined, but depending on how you calculate it, you can get slightly different numbers. The trend ultimately is pretty much the same, but you'll get slight variations depending on how we calculate it, because it is ultimately just a comparison. Allegedly, one of the first places it was compared, is it recorded? Dang. I want to say it was Pauling, Linus Pauling, and what he did was took an average of the electron affinity with the electron ionization. Okay, so ionization, how much energy it takes to remove an electron. Electron affinity, how much it takes to attract an electron. Okay, and by combining those two, he created the system of electronegativity, at least one of the early ones. Okay, which then takes us to assign some oxidation numbers to the following compounds. You got it. This is a blue box officially, so it's all on you. For those people struggling where to start, how do we start? Thanks for jumping in. It's really hard to hear what you were saying because you were all shouting so loudly at me. Valence electrons minus electrons owned. All right, this is done per atom. So in the interest of time, as we continue to advance, we should have all of our oxidation states now identified up on the board. Okay? I didn't show any of the work. You should be able to set up that work behind it. Okay? Remember, we do have an internal check. That internal check is that this has to sum to equal our overall charge. None of these show an overall charge, which means our overall charge must equal 0. So for that very first one, we might say, well, Mike, you screwed up, because if I add those together, I get a -3. Except we have to acknowledge how many hydrogens are there. There's 4. Okay? So when we're dealing with this, hopefully what you start to notice is that we'll get a formula. We take the number of one atom, we'll call it A, times its oxidation number or state, plus the number of the next atom times its oxidation number. You can do this for as many atoms as you have within your formula. This then must equal your overall charge. Okay? That formula will be consistent, even if it's a charged species. Because if it's a charged species, your overall charge is no longer going to be 0. You'll go through and identify it as a different number. Okay? My 2 cents is you always calculate oxidation state. There are plenty of cases where it's trivial. Okay? I would argue you should get in the habit of always calculating it, and charge being something that's always given to you. Okay? If you have that mindset, it should minimize the mismatch between oxidation state and charge. It is a very confusing topic to align. So confusing, I had a colleague say that there was no difference between them. Okay? Legitimate colleague who'd been teaching for 20 plus years, never mind what they'd been doing as a graduate student. Okay? And they said, there's no difference between them. There's very clearly a difference between them and what they apply to. It's ultimately a definition, and that's where it can become confusing. Kind of makes sense? Cool. Now that we've got numbers up here, I want to call your attention to a couple patterns, a couple other patterns. Okay? What did you notice was the oxidation state for oxygen? It was 0 when it was bonded to oxygen. That's true. But in our other cases, it was -2. So one of the rules that you'll sometimes hear is that oxygen is always a -2. Okay? It's not always, okay, but it is very, very, very common for it to be a -2. Again, why? It's the second most electronegative element on the periodic table. That's why. So in the vast majority of cases that we see oxygen, it's being bonded to something that is less electronegative than it, which means it's going to come in a -2. You see oxygen in a compound, -2. Okay? Again, be a little bit wary of what it's connected to, but that works. The other thing I want to point out is we had a definition, right, when we talked about our oxidation and reduction, right? What was the definition I said for oxidation? Sorry, that's going to make you go to Leo and all that. What was the history behind the term oxidation? Bonded to oxygens. Okay, whoops. If we look at CO2, we can't bond any more oxygens. That is as tapped out as we can get as far as the bonds to oxygen go. And we're at a +4. And we talked about reduced. Reduced was removing bonds to oxygen. Methane, CH4, is about as reduced as we can get. Anybody notice anything interesting about the oxidation number for carbon when we compare those?
It goes either positive or negative.
Positive for when what?
When it's with more electronegative.
Cool, nice change to your definition. We're looking at positive values when you're bonded to more electronegative elements, and negative when it's bonded to less electronegative elements. If we were going to look at oxidation, what was the other one? It's oxidation and reduction. Another thing that we could look at when we think about reduction is what happens to its oxidation number. If we go from CO2 to methane, what did we do to it? We reduced it. What happened to its oxidation number? It went from a +4 to a -4, also known as reduction. We're reducing the oxidation state. Okay? That can help as a way also to kind of memorize and see that system. Make sense? Okay. So general guidelines, oxidation numbers must add up to the overall charge. Neutral elements will always have an oxidation number of 0, okay, because they, by definition, own the same amount of electrons as they came in with. And then monatomic ions, the oxidation number is equal to the charge. Okay? I don't like that last one because it makes people think you got to memorize something. Apply rule 1. How many magnesiums show up in that formula? In that formula, how many times do I see magnesium? Once. Times an oxidation state. Oh, I don't know what it is. What does this have to equal? The overall charge +2. What's the oxidation state? +2. So I would make the argument that this last one is a silly thing to tell you because you've got the formula system behind it. If you're in the pattern of always solving for your oxidation states, ta-da! It's there. I don't have to memorize this extra rule. Why? If you memorize that extra rule, it becomes a rule that you might screw up. So minimize the amount of memorization to be able to build this out. Okay? And I always forget, you guys don't have to necessarily memorize things, but this would be useful things that you could take down as notes for how to go through and solve for oxidation states. Okay? Periodic trends and oxidation numbers. Right? So this is, I believe, Jackson, I think is what you were saying. You could try and look for trends and what those oxidation numbers are. Okay? Those oxidation numbers will tend to track with electronegativity, but you will find that there are certain cases where you don't get common states. This particular figure is interesting, but I would also argue it kind of defeats the purpose. Periodic trends, because we go through and look at it in trends and really zoom in on each of those individual charts, what you'll end up finding is that a lot of your elements have multiple oxidation states. Okay? That makes it more difficult to see a trend if this shows all the possible oxidation states for that individual element. Okay? So I'm nervous about this as a trend. What it's trying to get at is the more electronegative the element is, the more likely it's going to carry its ionic charge. Okay? Or the extreme opposite, the extreme unelectronegative or less electronegative, the more likely it carries its ionic charge. You run into cases in the transition metals, and that's where all the fun starts. Transition metals have charges up the yin-yang, okay? So they will have all sorts of different oxidation states, and those become more challenging to memorize or work with. Okay? So typically, you would have been told to memorize your charges of +1, +2. Does this sound familiar? I got at least one head shake, yes. Okay? Or -3, -2, -1. Right? And then I would argue, personally, you should also memorize aluminum, zinc, cadmium, and silver, because those are typically tested on +3, +2, and the silver is a +1. Right? Just pointing out the things that I would suggest should be familiar. Okay? Kind of makes sense? Think you can do some more? Or are you done with oxidation numbers? Silence is acquiescence, so you get to do more. At least in this class. Let's erase that one because that one was dumb. This is more like what I would have expected to see for oxidation states, so I was definitely surprised to see structures drawn in. Which was extra interesting just walking around looking at what you all were doing, particularly when we got to the nitrate, because everybody was trying to draw out nitrate, or some people were trying to draw out nitrate, other people were going based solely off of the ionic charges. And that's where we have to be extra careful when we process these things. So this goes all the way back to 151, dealing with complex ions. Ideally, those things would be memorized so that you could then apply and build this outwards. If they hadn't been memorized, you don't know where those pieces are, and you now fall into a trap of how do I segregate all that information away from each other. So if we go through and look at that first one, the aluminum hydroxide, you've got aluminum and hydroxide. That's going to split into Al +3 and hydroxide with a -1 charge. How do I know the hydroxide should have a -1 charge?
It can only lose one.
Say again?
It can only lose one for like what's located.
Hydroxide? You're talking about where hydroxide is located on the periodic table? I'm confused.
Oh, sorry. No, so I was thinking the wrong one on that. So aluminum
Okay.
has to lose 3 electrons
Why?
because it's also where it's on the periodic table. Since it's in the 3rd row, it most like it goes left to reach like a helium state.
So what you're using is the ionic charges. Are you allowed to be using the ionic charges to predict these?
Yes,
Why?
it's working for me.
Okay. When were you allowed to use the ionic charges? When it's an ionic compound. How do you know you have an ionic compound? A metal and a non-metal. Aluminum's a metal. Hydroxide's not a metal. So you're now in a system where it's an ionic compound. Because it's an ionic compound, you can split that into the individual ions. okay? Which then sets you up with this category. Have you memorized what aluminum's ionic charge is, or recognize how to find it off the periodic table? Or do you recognize hydroxide as having a -1 charge? Okay? Either way, you had to have something memorized to be able to build from. Does that make sense? Once it's split into the ions, we then have now arguably two questions. Okay? I want to look at the oxidation state for the aluminum +3. Well, there's one aluminum times its oxidation state has to equal +3. The oxidation state must be +3. What happens when I move to the hydroxide? So, well, what happened to the 3? Well, the 3 was to deal with the compound. I'm not looking at the compound anymore. I'm just looking at the hydroxide. And when I shift to now looking at just the hydroxide, I have one oxygen times its oxidation state plus one hydrogen times its oxidation state. This has to equal a -1. Okay? That's two variables with one equation. That's a problem to go through and solve. How do we figure that out?
We know oxygen always goes to -2.
We know that X, our oxygen, is going to be -2 because it's not bonded to oxygen or fluorine. And as soon as we know that drops to a -2, we get plus y equals -1, and we would get y equals +1. We said y was our oxidation state for our hydrogen. You track? Okay. If we go through and look at the iron oxide, how do we go through and do that one? You can do the same thing. It is technically an ionic compound. That one as an ionic compound becomes a little bit trickier because iron's not one that you're required to know the oxidation state or the charge for because it has multiple different charge states that it could apply to. So instead of breaking that one up into the ions, what I would recommend is 2 times its oxidation state. I don't know what the oxidation state is for iron. Plus, sorry, I forgot the formula, 3 times the oxidation state for oxygen. This has to equal the overall charge of 0. Okay? Since I know oxygen is not bonded to oxygen or fluorine, I'm now looking at y equals -2. -6 plus 2x equals 0, and I get x equals +3. What did you say it was?
I said that.
Okay, I just checking.
Yeah.
Does that make sense? As I talked through it, I would have challenged me. Does anybody want to challenge me on anything I said? It did go by kind of fast.
The first one doesn't still have to equal 0, or it doesn't.
So you're doubling back to the first one?
Yeah, so-
Okay, we can double back to the first one. So if x is a -2, y is a +1, and the aluminum's a +3, well, does that not equal 0? I mean, +1 minus 2, that's a -1, and +3, you're right, that doesn't equal 0. What did we miss? If you're going to go through and look at the overall charge for that entire compound, what we'd be looking at is the aluminum at a +3, the oxygen at a -2 times 3 of them, plus 3 times the hydrogen at a +1, and you'd add all of that up. That's where you're getting the 0 from. So it does still check out as a 0. Okay, the thing that I would have challenged, potentially, though it did go by real fast, as I said, since the oxygens aren't bonded to oxygen or fluorine, how do you know the oxygens aren't bonded to oxygen or fluorine? Does anybody know the structure for Fe2O3? There's definitely no fluorine, but couldn't I have an oxygen bonded to an oxygen in that? Do you know the structure of that? Said another way, I don't know the structure of that. Okay, so how do you know that you can go through and do that? I would make the argument that you don't know that, you just have to make that assumption to navigate this question. Okay, unless you're given the structure, you assume they're all the same. Okay, which is a horrendously dangerous assumption. But if you don't have broader context, there's nothing you can do about it. Make sense? Last one, we split into lithium and our nitrate. Our lithium's going to come in as a +1, the nitrogen's going to come in as a +5, and the oxygen will, again, be a -2. Okay, assuming I did that math right. All right, officially, I just did that all in my head, but I did it all in my head because we're done.